Let's trace a program step by step. This is a common pattern we'll use to understand what the computer is doing under the hood when we press the run button. Tracing program execution like this helps us better read and write programs because we can start to predict what the computer is going to do with each instruction. Let's trace a program instruction without having to go through a long process of trial and error. For now, we'll write this all out together so we can make sense of what's happening here, but eventually we'll get familiar enough with Python where we can trace small blocks of code like this in our heads. When you press run, the computer looks at your program line by line. It isn't smart enough to zoom out and look at the big picture and try and understand what the program is trying to do as a whole. When I say line by line, I literally mean that the computer is going to load each line of your program into its working memory one by one. And then with one instruction loaded into its working memory, it's going to interpret that instruction in isolation, in total isolation. Now, remember that the computer is not a mind reader, so it doesn't understand any nuance or intention behind your instruction. It's only going to do literally what that instruction says, according to whatever rules of Python. Let's see that in action by tracing this program. The computer takes the first line of the program and loads that into working memory. Then the first thing it's going to do is look for any expressions to evaluate. Remember that evaluating an expression just simplifies it down to a single value. Here we have the expression, the integer 4 plus the parentheses to take and print to move to remove. Print, there's 1. But they're going to evaluate this expression in more working memory and it's not the expression, the integer 2 plus 2. Because working memory. Then it jumps to the next line of the program and oh, there is no next line. We have our final result here in the console. Want to check my work? Copy this program into a code editor and run it for yourself. Is the result the same? Debugging is just a fancy term for fixing errors. Debugging is just a fancy term for fixing errors in programs. It's the process of removing bugs, so we call it debug. Since it's something we'll be doing often, let's learn how to work together with our IDE to track down and fix bugs in our programs. Here's a program I've been working on to calculate office expenses over the course of a month. You'll notice that there's a linter error over here, so that's probably already a good hint that I have a syntax error somewhere in my program. But before I get too far ahead of myself, let me just hit run and see what happens. Alright, suspicious. Suspicion confirmed. The console says we have a syntax error. Remember that a syntax error means that our code is invalid Python. The first part of this message is what's called a stack trace. A stack trace traces or identifies the location in the program where the error originated. The computer is telling us that the error is coming from a file called main.py. As we can see over here, this is the name of the file that we're working in. This part then tells us that the error is coming from line 2 of that file. For our convenience, it copies line 2 into the stack trace, but we can also go over here in the code editor and look and see, this is line 2. This little caret in the stack trace is pointing to this quotation mark character. Same thing with the linter, it's kind of pointing toward the end of the line here. The last line of the error message is the most important. This is where the caret in the stack trace is pointing to this quotation mark character. Same thing with the linter, it's kind of pointing toward the end of the line here. The last line of the error message is the most important. This is where the computer tells you what type of error it is, in this case a syntax error, and then it makes its best guess at what the cause of the bug is. Now, that guess is not always 100% correct. You'll have to use your judgment here, but it's usually a good starting place. This error message says unterminated string literal. Naturally, error messages tend to be worded in kind of obscure computer speak, so let's try and translate what this means. If you're not familiar with a particular error, sometimes the easiest thing to do is copy and paste that last line of the error message into a search engine and see what other people say. Okay, so I'm looking up unterminated string literal Python, and I see here someone explain it as when you forget to close the string with a matching quote. Okay, that makes sense. This little caret here is pointing at this quotation mark character, and that's next to another quotation mark character. And so why do I have two? I have mismatched quotation marks. So if I just delete this, then I have a string, and then let me try running it again. Boom, okay, that error message went away, and so did the linter error, but now I have a new error. Let's try debugging this one. Now, this error message just says invalid syntax, so that means the computer doesn't really have a best guess at what's going on. It says, perhaps I forgot a comma? I don't really understand. Why would I want a comma here? I don't know. Let me try putting one in and running it. That still seems wrong. Okay, I'm going to undo that. I'm a little stumped on this one, and the computer's not really offering much help. So one strategy I can use is to comment this line out. We know that the computer doesn't execute lines of code that are comments. I don't want to just delete this line because I do want to fix it at some point, but maybe I'll come back to it later. So what I can do is stick a comment character, this little hashtag in front of this line, to turn it into a comment. And that means when the computer runs the out that line, the linter error jumps to line 14. The lint message says, and there shouldn't be. Everything needs to be lined up with the left margin. So let me just delete this space real quick. Now I'm seeing a runtime error. I know it's a runtime error because the output from the first few print functions is showing up in the console. That means that the computer started running my program because it ran these first few lines, and it only got stuck when it got to line 7. This is another one where I'm not really sure what this wanted this line. Looks like my program is now running without an error, but I did comment out that one line before, so let me go back and try and figure that syntax error out. Okay, now that I'm looking at it again, I noticed that there's something going on with the syntax highlighting. Week 2 expenses is black, and it should be green because it should be a string, right? Because I'm trying to print out a string. Okay, I need quotation marks around this thing. Amazing. Okay, I think I have fixed all of the syntax errors and runtime errors. Am I done debugging? Nope, I haven't checked for logic errors yet. Let me step through this output and make sure that the results all make sense to me. Okay, I'm printing out a heading for the report. Then I have miscellaneous expenses, 5644, that seems within reason. Week 1 expenses, that number seems within reason. Week 2 expenses, why are there 3 decimal places here? That's not a legal price value. Let me go to the line of the program that's calculating that sum. Interesting. I have the price 18.412 here. What is that number supposed to be? Looking back at the utility bill for that week, it looks like that number is supposed to be $184.12. So let me just fix that. Cool, let's continue checking the rest of the output for logic errors. We have week 3 expenses, and that number looks good, and that's it. My program finally works. Next time though, When we run a program, the computer executes each instruction line by line. Then, when it finishes with an instruction, it clears out its working memory, so the computer has forgotten what it just did by the time it gets to the next line. But what if we want to remember the result of a calculation across lines? We need a way to tell the computer, hey, remember the result of this instruction this time. I'm going to need this value later. To do that, we use variables. A variable is a reserved location in the computer's memory for storing a value. We associate each location with a name, so it's easy for us as the programmers to refer to a specific location later. We can also update the value that a specific name points to over time. Because we have a name, we can ask the computer questions like, what value do you have stored at location view count right now? To create a new variable, or update the value stored in an existing existing variable, we'll use an assignment statement. An assignment statement starts with the name of the variable on the left-hand side, then an equal sign, also called the assignment operator, and on the right-hand side, the value to be stored. We read this statement as the variable view count is assigned the value 324. When the computer executes this instruction, it'll go off to its short-term memory and look for a label with the name view count. If it doesn't find one, it'll set aside or allocate a new chunk of its memory, and then label that location with the name view count. Finally, it'll store the value on the right-hand side of the assignment operator in that location. If it does find that label, it will allocate a new chunk of memory, store the new value there, and take that label from the old location and move it to point to the new location. That old location is now unreachable. There's no way for you as the programmer to ask about that location in memory anymore because it doesn't have a name. There's no need for the computer to keep this around, so it just erases it. Anytime we want to access the value stored at a location, we can ask the computer to retrieve it by giving it the name. For example, if I had the and memory anymore, Anymore because we have a name, we can ask the computer questions like, what value do you have stored at location view count right now? Relation across lines. A variable is a reserved location in the computer's memory for storing a value. We associate each location with a name, so it's easy for us as the programmers to refer to a specific location later. We can also update the value that a specific name points to over time. Because we have a name, we can ask the computer questions like, what value do you have stored at location view count right now? we'll use an assignment statement. An assignment statement starts with the name of the variable on the left-hand side, then an equal sign, also called the assignment operator, and on the right-hand side, the value to be stored. We read this statement as the variable view count is assigned the value 324. When the computer executes this instruction, it'll go off to its short-term memory and look for a label with the name view count. If it doesn't find one, it'll set aside or allocate. We can ask the computer to retrieve it by giving. Next time you run the program, the computer starts fresh again. You can think of it after line 4. When the program terminates, the computer clears out all these locations in memory. That means the computer executes this instruction, it'll go off to its short-term memory and look for a label with the name view count. If it doesn't find one, it'll set aside or allocate a new chunk of its memory, and then label that location with the name view count. Finally, it'll store the value on the right-hand side of the assignment operator in that location. If it does find that label, it will allocate a new chunk of memory, store the new value there, and take that label from the old location and move it to point to the new location. That old location is now unreachable. There's no way for you as the programmer to ask about that location in memory anymore because it doesn't have a name. There's no need for the computer to keep this around, so it just erases it. Anytime we want to access the value stored at a location, we can ask the computer to retrieve it by giving it the name. For example, if I had the instruction print view count, the computer would go find the memory location view count, grab the value stored there, and substitute it in. So this would print 324. Remember, instructions in a program execute in order, so the value stored in a certain variable might be different at different points in the program. For example, after the first line executes, the location view count contains the value 324, but after the third line executes, the location view count now contains the value 501. So when I access view count on line 2, this prints 324, but when I access view count on line 4, this prints 501. Note that after line 4, when the program terminates, the computer clears out all these locations in memory. That means the next time you run the program, the computer starts fresh again. You can think of variables like mini whiteboards. When you create a new variable, you go off and get a new whiteboard. You give that whiteboard a name, and then you write a value on it to store it there. You can create 100 variables, which means you went off and got 100 different whiteboards. And if you want to know what value is stored on a specific whiteboard named color theme, then you look for the label color theme, grab that whiteboard, and look at the value written on it. If you have a second or third assignment statement for the same variable color theme, the computer doesn't go off and grab a new whiteboard because then it would have 2 whiteboards labeled color theme, and that's confusing. Instead, it grabs the existing whiteboard named color theme, erases the old value on the front, and then in its place, writes down the new value. When the program terminates, we erase all the whiteboards, peel the labels off the back, and put them neatly back on the shelf where we found them, so they're nice and clean for the next program execution to use. How might we use variables in a real program? Say we're building a game. What data might we need to keep track of? Well, we might need to remember the player's current score, what level they're on, and what character they selected. As the program runs, we'll need to update these values over time. Like maybe when the player collects an item, their score increases by 5. If we want to be able to ask the computer what's the player's current score at any point in the program, we need to tell the computer to store that value in a variable. Some games might have hundreds or thousands of different pieces of data that they need to keep track of, which means hundreds or thousands of different variables. Think closely about a piece of technology you use every day, like an app or a game or an appliance in your house. What data is it keeping track of? What variables might it have? As you learn to think like a programmer, you'll start seeing variables everywhere.